So the first thing we need to consider with circular motion is angular displacement. So we could use degrees, which we're very familiar with, but very often we use radians. So you may have come across these possibly at GCSE, but certainly if you're doing maths A-level. So we do need to know the definition, which is written here. So 1 radian is the angle subtended at the center of a circle by an arc of length equal to the circle's radius. So it's quite a complicated word, subtended, but it's quite useful because it basically means this angle here. So if we have an arc length here, which is equal to the radius, then it's the angle between here of this little triangular segment here. So 1 radian is approximately 57 degrees, and you probably know already that we have 2 pi of these in 360 degrees. So remember that pi is a number, 3.142, so it's 2 times that. So it's not a round number. It's quite, yeah, this is why we use pi. So we have to convert between degrees and radians. So if we're going in this direction, we need to either multiply by 2 pi and divide by 360. So what we're doing here is we're getting rid of the degrees by divided by 360 degrees, and we're multiplying by the equivalent of radians. So this is our conversion. So sometimes we just do half of that, and we multiply by pi and divide by 180. So you definitely need to be confident with converting between degrees and radians to degrees. So I recommend you pause the video and just have a go at some of these here before you continue. So let's have a look. So 90 degrees. So if we have nice easy fractions, simple fractions, then we can leave pi in the answers, or we could write this as a decimal. Normally, because physics is a practical subject, we would think about significant figures and decimal places, but it's normally acceptable because pi is a very recognized number to write this as pi over 2, but we could write this as a decimal as well. So that's obviously half of 180, so it's going to be half of pi. So 30 degrees is 90 divided by 3, so that'll be pi over 6. So again, if we have a nice simple fraction, we can leave pi in the answer, but if we have something which is not a simple fraction, then we'd have to use our conversion here to get a decimal answer. So we multiply our 174 by pi, divide by 180, and we get 3.04. Going back the other way, so converting into degrees, then here we've got pi, so we oops, this isn't working, one moment. Yep, so if we're converting into degrees, so we have pi, so that is half of a circle, so that's going to be 180 degrees. Pi over 3 is going to be that divided by 3, which is obviously 60. So again, if we have simple fractions, then that makes life a bit easier. But if we have an actual decimal, then we're going to have to use what we have here, our conversion. So it's going to be the opposite of this. So it'll be multiplied by 180 and divide by pi, and we should get our answer of 43. Okay, so let's look at the relationship between angular displacement and angular velocity, and also this very useful little formula here. So you may have come across this before. Theta is equal to S over R. So what we're saying here is the angular displacement is going to be related to the size of the arc length. So obviously as S gets larger, then theta will get larger in proportion. So we can derive where this comes from, and we'll do that in a moment. But generally we can just use this relationship, which is very helpful. Angular velocity, so that's a very important term, given the symbol W or omega. So that's defined as the number of radians per second. So this is why radians is quite important. So our first formula, omega is equal to delta theta over delta t. So that is basically the algebraic equivalent of what we have here. So theta in radians divided by time, that will give us radians per second. Okay, so that is a formula given in the formula booklet. We can also write this as 2 pi f, and we can link these two formulas together if we wanted to. So again, if we're talking about the number of radians per second, if I know f, which is the frequency for one complete circle, one complete oscillation, then if I multiply that by the number of radians in one circle, that will give me the number of radians per second. So again, we can define this one, omega is equal to 2 pi f, based on the definition. The final formula we have here is V is equal to R times omega. So that's the linear velocity. So the velocity at a particular point, the velocity tangential to the circular motion, will be equal to R times omega. Again, nice simple formula. So we should be given all 4 of these in your formula booklet, so just double check that your specification provides these. We're not expected to derive them, but we can do, and we may do that later on in the topic. So for example, this first one here. So if we know that the arc length is related to theta and it's going to be proportional in size, well, the arc length is going to be a fraction of the circumference, and that will be the same fraction as theta is a fraction of 2 pi. So s divided by the total circumference, which is 2 pi r, will be the same as theta divided by 2 pi. So if we work out the arc length, that will be the circumference multiplied by this angle as a fraction of 2 pi, so theta over 2 pi multiplied by 2 pi r. 2 pi is going to cancel and we have r times theta. So we can derive this. That might be useful, but most specifications would not insist that you do that.